Okay. So, we continue our discussion and then we have found out that this is the third eigen frequency or eigen vector, and we see that these two are equal and this one is negative opposite in sign and there is a scaling factor. So, it means actually two masses they are going. So, two outside the smaller atoms they are going together like this or like that, and when they are moving on this side the bigger mass moving in the opposite direction, where they are moving in like this one is moving in the opposite direction. Okay. So, we will give you a little detailed description of the same, but first let us try to normalize it. Now, this 3 you see there is an x, there is an y, there is a z, and these 3 are arbitrary. We have not given any, we have not decided on any value of this matrices, these quantities. But what we can do is we can always find a means to normalize them, and okay, how do we normalize it? Please recall AL transpose A M is equal to delta L. So, this is our tool for normalization. What we are going to do is, and if you, so we are going to construct, for example, with A 1 we are going to write x square 1 1 1 m capital M 1 1 1 is equal to 1. This is just this relation opened the bracket. So, I wrote it in an explicit form. Now, there will be an x from the transpose vector, vector and x from this side vector. So, I just put an x square here. So, x square or x is the something which we are looking to find out. Now, if I perform this calculation, this will be x square. See, the first one it will be 1 1 1 m capital M m equal to 1, which will be x square m plus m plus m, this is equal to 1. I am just doing it explicitly, probably you already know how to do this calculation. Please recall that it is a 3 cross 3 matrix. Please notice that it is a 3 cross 3 matrix, it is a 3 cross 1 matrix, it is a 1 cross 3 matrix. So, this will reduce it to a 3 cross 1 matrix, this is a 1 cross 3 matrix. So, eventually the final answer will be a single number 1 cross 1. So, x is 1 by root over, this is 2 m plus m, right. So, this is the value of x that you have got. Now, in this case it is not terribly important, because anyway this is a translation, it is not a true vibration, but just to show you, just to demonstrate how it works, this is the value of x. So, if you want to write the normalized value, so you have to write a 1 is equal to 1 by root over, or rather I will just write little closer, that is easier for the camera, 1 by root over 2 m plus m 1 1 1. Good. Now, let us repeat the same procedure for this one. It will be y square, capital Y square, it will be minus 1 0 1, similarly it will be minus 1 0 1. Okay. So, following the same procedure, we get y square is equal to, or y square times it will be so first it will be minus 1 0 1, second it will be minus m and m, 0, okay, which will be equal to 1. So, y square times, so it will be m plus m, 2m, which will give you y is equal to 1 by root 2m. Okay. So, in this normalization the capital M does not enter, because there is no motion. As I said, for this mode it will go both together out or together in the side molecules. The central molecule will remain stationary. So, understandably there is no scaling, there is no association of capital M with the normalization constant. So, if I write it, it will be 1 by root twice m, 1 minus 1, or it could also be plus 1 minus 1 here, and there is a 0 in the middle. And for the third normalized eigenvector, we have to write z square with 1 minus 2m by m, 1 minus 2m by m, 1, right. So, second step, will be m minus 2m m equal to 1, and then we have z square times m minus 4 m square by m plus m. So, it will be 2m equal to 1. Okay. So, z will be equal to 2m 1 by root over 2m 1 plus 2m by m. Is it correct? Is it correct? Oh, I have made it, I did it correct. Okay, great. I am doing well today, very good. So, A3 is equal to 1 by root over 2m 1 plus 2m by m, and 1 minus 2m by m 1. Okay. So, this is the third eigenvector. Right now we have, so we started with 3 frequencies, 0, root k by m and root k by m plus 1 by 2m by m, and we have found out 3 normalized eigenvectors. So, that means the problem is in principle solved, kind of, not completely yet, because we still have not officially declared what is, I mean, as in mathematically we have not proved what is normal modes and all. But let us once again let us look into the details of this motion. See, I am taking time in this example because it is something which is very intuitive. This example is easy to grab. Okay, its calculations are slightly longer, but it is not complicated, and also it is very visual, this one. Other examples might not be that visual. Okay. So, this is my molecule once again. So, we have m, m and capital M here. Now, what happens? What happens when there is a translation? There is a translation means all three moving in the same direction, either this direction or that direction. That is very straightforward. So, this we understand. For this one we have seen that 2 are moving in opposite direction and 1 is stationary. So, the central atom is stationary. Let us say this one is heavier and these 2 are lighter. So, this one moves out or move in, whatever they do it in a synchronized manner. with a frequency k by m, and that is also very easily understood, because see root k by m is the frequency. If I replace this with a solid wall, the frequency of this spring mass system will be root k by m. Because this central atom is not moving in this particular frequency mode, when so this is the definition of normal mode. Normal mode is a particular type of it is a very particular motion in which system oscillates with one single frequency. There is no multiple frequencies in normal mode. So, when the system oscillates with only one frequency, then only this particular frequency, then we have this one stationary, as if you can think of it as if you replace this with a wall, solid wall, and these two masses are moving independently, but not exactly independently, because there is a very steady phase relation of 180 degree between these two. So, either again that is also relative, because they are on other sides of this particular molecule, we are thinking that they are going out 180 degree, but if you think of it as a two independent systems, they are exactly synchronized. Anyway, so this is one motion, and for the third motion so we understand this. For this one, you see two molecules, two atoms, they are moving in a same direction at a given instance of time, and the middle mass, what is it doing? It is going opposite with a scaled amplitude. If I try to explain this, right, or so these two are either going like this or going like this, and if these two are going like this, the middle one is moving this way. If they are going like this, the middle one is going this way, with a scaling in amplitude which is given by 2m by m, right. Now, why so? This is why, because there is another very interesting property of normal oscillation, normal mode vibration. Please remember, this property is specific to vibration. Okay. For translation and rotation, it might not be valid. And that particular property is the center of mass in a vibration, normal mode vibration, should not move. So, what is happening here? When for the first one, it is a translation, so it is not a vibration, that particular property is not a valid property. For the second one, when this one is stationary and these two are moving, see, by symmetry of this system, if they are all identical, if we have two identical masses with two identical spring constants k, the center of mass is exactly on this particular atom, right. So, when these two are moving out or coming in together, the overall center of mass position is not changing. Okay. Let us try to formalize it a bit. Let us say, okay, I will just call them, this is my origin, let us call this x1, let us call this x2. If this is the case, or please remember that if this is x1, sorry, if this is x1, this will be minus x1, because this is my origin. I am just taking this just for convenience. So, the center of mass at equilibrium position will be m. What is the relation for center of mass? Sum over I m I r I divided by sum over I m I, right. So, the lower sum will be 2m plus m, and we have from here we have x1 minus x1 times m plus 0 capital M. This will also cancel, which will give you a 0. So, center of mass at equilibrium is at 0. Now, if you for the first type of motion, if you boost the center of boost the position of this two, increase the position of this two by delta x. So, this will be x1 plus delta x, and this is minus of x1 plus delta x. It remains the same, because this two anyway cancels out. Now, for the third motion, what happens for this particular frequency? If this has gone by delta x, let us say, if this is gone let us say in this way x plus delta x. So, this one will be x 1 minus of x 1 minus delta x. Okay. And from the normalization from this relation, does not matter if it is normalized or not, from this relation we know that, okay, so we are discussing a situation once again, we are discussing a situation, do not be confused, we are discussing a situation where this one is going this way, this one is going this way and this one is coming this way. Now, this one will not be 0 anymore, but it will be minus 2 m delta x by capital M, right, because this one, okay, I will just open the bracket and write here, this one was minus x 1 and plus x 1, this is minus x 1 plus delta x, this is plus x 1 plus delta x. So, this is minus 2 m by m delta x. Now, you calculate the center of mass, okay, total mass I am not interested, that will remain the same anyway, I will just put 1 by 2 m, okay, so let it be there, does not matter really. Now, this one is x 1 plus delta x m minus x 1 plus minus delta x m plus 2 m delta x. This capital M and M will cancel out, and if you do that, now after this, see, first term will cancel out, second term will cancel out. So, it will give you a 0 once again. So, it will be equal to 0. So, and this x delta x we have taken at any instant of time. We can also take x 1 minus x, the calculation will not change. So, whatever we do, the center of mass for, okay, for this frequency it is very intuitive, because this one is not moving at all and these two are moving out simultaneously or coming in simultaneously. So, the center of mass is stationary. This one, both, all three masses are moving. Even then we can show you, we could have shown systematically that we have shown systematically that the center of mass is stationary. So, that is another property of normal coordinates. Okay. I will come back to that in a moment, formalize the normal coordinates, but let's first tell you, let me tell you that these two modes where the two atoms, two side atoms are moving in or out simultaneously, it is called the symmetric stretching. And this one where two are moving in one direction, the other one is moving in opposite direction, it is called asymmetric. Asymmetric stretch of a linear triatomic molecule. Now, it so happens that these modes for certain molecules, for example, carbon dioxide molecules, they can be measured exactly using spectroscopy. And these modes are what, some of these modes are responsible for the carbon dioxide laser. So, we have certain frequencies in laser, right. So, in what happens in a laser is that we have an optical cavity, we have certain frequency, and if that frequency matches with the natural resonance frequency of this optical cavity, then we can boost, by stimulative absorption of radiation, we can boost this particular frequency and we can send a spark. So, this is these modes, the symmetric stretching modes and antisymmetric stretching modes and also bending modes of carbon dioxide molecules are responsible for different frequencies of carbon dioxide laser. Now, in molecular spectroscopy also for many triatomic molecules, we can actually measure the symmetric and antisymmetric stretching modes. So, this is something which is more practical. So, more than theoretical aspect of it, and it has been found out, although they are very small systems, they are quantum mechanical in nature, the classical picture is not very far in terms of frequencies to describe the motion. So, if possible we will take up some of this, I will show you some of these examples of real world spectroscopic data, but let us first formalize the or finalize our discussion on normal modes. Okay. So, keep this in mind, we will come back and use this relation. See, q k is given by sum over L A L e to the power I or P L, right. Is it right? Yeah, that is what we have written so far, but let me tell you this is not completely right. There are two terms missing. First of all, there will be a C L here, I will explain this, and secondly there will be a theta L here. Why? Why these two constants, additional constant? See, what we have found out so far are the normalized part. So, this is something which will give you the quantitative description or rather qualitative description of the problem. Right now we have just now we have discussed the symmetric stretching and antisymmetric stretching of a triatomic molecule. I can tell you by virtue of this normalized eigenvectors, I can tell you that what will be the proportion, I mean what will be the relative motion between these molecules. But what is the magnitude of it? Nowhere in this discussion, in this expression you cannot find any any number which is responsible for the amplitude. The amplitude could be 5 millimeter, it could be 5 centimeter, it could be 5 meters, nothing is mentioned here. So, nothing is associated with the system size except system masses are included definitely, but the length scale is not included. That length scale will be included there. Also, I can look at it this way. We have certain boundary conditions to begin with. So, let us say one molecule, one triatomic molecule is in equilibrium position. So, if we start the oscillation, if we just displace one of the masses from equilibrium and let it go, only then it will oscillate, and that leads to some initial condition. Now, that initial conditions has to be included somehow in the final solution, right. Right now, we have found out only this part A and PL, AL and PL, which gives you a very good quantitative idea of the motion, but will not give you qualitative idea of the motion, but not give you a single idea of what is the actual magnitude of vibration. Also, there is a phase factor, right. So, if we move it, if let us say we have this as my initial configuration. Okay. So, if I initially let us say I have taken this one in this direction and this one in this direction. So, that means we are stretching this spring and compressing that spring, and then I let it go. Which mode of vibration will that be? I mean, which mode will be activated? Will it still remain in the anti? So, moment we release it, these two masses, this mass will start going inside and this mass will start moving outside. So, that means they are going antiphase, antisymmetric stretching. Okay. But also what we can do is we can also give a displacement, arbitrary displacement of this and let it go. So, we do not know what will be the phase relation unless and until, and phase relation due to the initial condition unless and until we include this theta L here. So, a most general description will include of C L and theta L, where C L, theta L are determined by initial condition. IC means initial condition. Okay. So, now that is something which gives you a complete description of the motion. So, we can write this as A L sum over L. So, sorry, there will be a K L all this time, A K L Q L. Okay. So, we can define Q L, which is equal to C L e to the power I P L T plus theta L. Now, in some of the books you will see that instead of this only the cos term, cosine term has been taken. That is also a valid description, because the people use logic like for real measurement, I mean for real life measurement, we are interested only in the cosine part. The sine part is imaginary, which is there, but which we will not be able to measure. Okay, so that is also a valid description. So, we define QL like this. Now, if I try to look at my kinetic energy matrix, which will be QK dot, or rather Aij Qi dot Qj dot. Now, in terms of this representation, I can write this as Aij AIL AJM, yeah, QL dot QM dot, right. Now, look at this term. This is nothing but delta LM, right. So, that we have seen, this is from the normalization. This is how we normalized ALs. So, delta M QL dot QM dot, which is, because L equal to M is the only possible solution. So, we can just write it as QL dot square. Similarly, potential energy equal to B I J Qi Qj, which will be B I J A I L A J M QL QM, which will be delta LM PL square QL QM, okay, which will be V will be simply QL square PL square. Okay. So, we see that both kinetic energy and potential energy. So, T is once again QL dot square and V is QL square PL square. So, in this new defined coordinate QL, which is given by this, if I define this as a coordinate, which is also a valid definition, because there is only one running index L, which is here and here as well, here, here and here as well. So, CL and theta L are from the initial condition, and PL is the normal frequency that we have to determine by solving this determinant. Now, if we do that in that representation, T and V, these matrices are completely diagonal, right. Not only that, if I now construct this okay. Now, these two are the matrices. Now, if I construct this Lagrangian, which is T minus V, which will be given by QL dot square minus QL square PL square. Okay. Now, in this Lagrangian, ddt of del L del QL dot minus del L del QL will be equal to 0. Now, if you do that, you will get QL double dot plus PL square QL equal to 0. And this is kind of obvious, the way we have defined QL, this has to happen. So, if we work in a new set of coordinate QL, by the way, this is a point transformation, the same Lagrangian which we wrote in terms of Q1s and Qy's and Qj's, we have reduced in terms of Q's, capital Q's, right. And in this particular, after this point transformation, not only the Lagrangian becomes a diagonal element, I mean Lagrangian becomes totally diagonal, and each of this is a discrete independent equation. So, what we have done here using this particular coordinate capital QL, we have diagonalized not only we have diagonalized the kinetic energy and potential energies, but also we could distinctly, we could write independent differential equations for different frequencies, and these are the theoretical definition of normal modes, right. So, we will do one thing, we will take it up from we will go back to this example of linear triatomic molecule and try to find out what are the normal modes here, right. Fine. So, for linear triatomic molecules, we have not written the final solution. We have written 3 frequencies, which was P1 equal to 0, P2 equal to root k by m, and P3 equal to root k by m 1 plus 2m by m, right? Am I right? Just give me a second, I will just check. Yes, good, right. So, these are 3, yeah. So, we can write in terms of the Cartesian coordinates q1, q2 and q3, we can write them as C1, or rather we can write them as C1A1 plus C2A2, C1A1 e to the power I P1t plus C2A2 e to the power I P2t plus C3A3 e to the power I P3t, right. Now, writing explicitly, it will be C1 by root 2m plus m 1 1 1, this will be 0 because P1 is, this will be 1 because P1 is 0, plus C2 by root twice m 1 0 minus 1 plus C3 by root twice m 1 plus 2m by m 1 minus to the power I root k by m t 1 to the power I. Okay, I will just write P3t. So, in principle, we can write Q1 expression for Q1, Q2, Q3. Oh, of course, there will be a theta 1, there will be a theta 2 and there will be a theta 3, right. So, it will be plus theta 2, I will be outside, plus theta 3. So, that is the most general solution. Get rid of this ones. Okay. So, this is my most general solution for a linear triatomic molecule. Any motion, if we are given boundary condition or initial conditions in terms of C1s and theta 1s, we can find out the instantaneous position of any of these coordinate. Okay. Now, in terms of normal mode, so what will be the normal modes in this case? We have to write QLs. If I have to write QLs, my Q1 will be, what is the definition? Go back to the definition once again, which is, sorry, QL is equal to CL e to the power I omega L t plus theta L, or rather PL, PLT plus theta L. If I follow this definition, my Q1 will be C1, I am not writing it explicitly, forget about the amplitude, it will be C1, there will be no amplitude term, plus C2 e to the power I root A by m t plus theta 2 plus C3 e to the power I this big term, this third frequency whatever P3t plus theta 3. So, this is my one normal mode. Similarly, I can write expression for two other, sorry, it will be, oh sorry, it will be C1 right. C1 e to the power IPLT plus theta L. Oh, Q1 will be simply C1. Sorry, my mistake. Q2 will be C2 e to the power IPL P2T plus theta 2 and same for Q3. So, these are my three normal coordinates. Okay. So, now we have solved this problem in principle in terms of both normal modes and we have found out the normalized amplitudes. So, this problem is in principle solved. Of course, unless and until we have boundary conditions, we cannot determine C1, CLs and theta Ls, which we will take up in one of the next problems. Okay. So, we have few more problems in the problem set and we have two more lectures in hand. We will see it, we will try to find it, we will try to solve it as soon as possible, and once these are solved, if we still have some time, probably we will revisit some of our previous discussion and go little bit more into the details. For now, thank you.